All right, well, thank you for having me today to kind of talk to you about, as the title suggests, weather and climate and some of the differences between these two topics, as well as understanding, using models and different observing platforms to understand patterns. Obviously, weather is highly dictated by patterns and why those occur in certain ways across the Earth, and just kind of give you some of the basics behind weather and climate, and just to get rid of the title screen here and show you this picture that I like. And I'm going to start here in obviously an Arctic region, and we're going to return here by the end of the presentation. So this is just a picture from northern Alaskan region, and it really encapsulates both weather and climate in this photo. So you can see, weatherman jargon, this is a partly sunny day. You've got some clouds in the sky. It's obviously probably a cold temperature today, so the temperature is cold in this location. And essentially that's what's happening right now as you see this picture. But trapped and locked in, say, the ice here in this glacier are keys to the climate, keys to the past, the long-term average weather conditions for this area. So this picture really captures the essence of both weather and climate, and that's what I'm going to talk to you about today. So I'm going to start you on a little journey, begin with a 5-year-old boy in Miami, Florida, as Tropical Storm Bob came across the peninsula. Kind of his first interaction with a major weather event that was occurring. A few years later, he moves back to Ohio with his family, and kind of experiences the summer of 1988. Many of you probably remember that summer. Kind of the first drought of this young man's life. And as this Time magazine front page captures, the big dry. It was kind of a pretty short-term but very intense drought event, right? So a year later, this young boy's feverishly watching the Weather Channel as Hurricane Hugo makes its way toward Charleston, South Carolina. Have a large amount of family in Charleston, South Carolina. This boy does, rather. And this gentleman here, John Hope, was the hurricane specialist at the time. And it was just fascinating to see what he was doing. Obviously, I let the cat out of the bag. And I wanted to emulate what he was doing, and he had a PhD. And this is really started like, well, if I want to understand the complexities of weather, I need a good deal amount of education. And so that's one of the events. And then as I got older, obviously into high school, I could research some local events, things that I became familiar with. My father actually went into Xenia aftermath and kind of helped with cleanup, so I had some of the personal stories like that. Obviously a very devastating tornado. And then every meteorologist loves, not Jim Cantori, but, oops.
Whoa! Was that lightning? Christina! We just had a thunder snow. We just had a lightning strike and thunder here in Worcester. It is snowing at over 4 inches an hour. We have 13 inches of snow on the ground. It is snowing at 4 inches an hour right now. We just walked down the street. We heard reports of some trees down. There's actually a tree down on a house.
You think he loves what he does? He absolutely loves it. And I'll give you a little story beyond this. So I've actually experienced thunder snow a couple of times. Once when I was a young child, but this past winter, I was at home and my mom lives right across the alley, and she's bringing me out a cup of coffee, and we had a huge bolt of lightning really close by, and I got all excited. She didn't understand why I was out there dancing and all this stuff. And I walk inside, and literally this event brought a 6'8" giant of a man to tears just because, just to experience this type of rare weather phenomenon. So if thunder snow doesn't get the passion going in meteorologists, then nothing will. All right, so let's begin talking a little bit about the weather. So a lot of you, everyone here obviously experiences the weather, but exactly what is it? So weather is what is currently happening outside, and it's a very short-term process. These are things that I think are tangible to everyone, right? We feel the sunshine. Hopefully we don't experience a tornado that comes through, but obviously that's another type of weather event. Snowfall, obviously, heat and cold temperatures, thunderstorm, rain, the forecast out for a few days, even weeks. That's what we talk about weather. These are short-term processes that are occurring. And there's a lot of patterns that we see as meteorologists that help us to predict the weather and help us to predict what's going to occur, what type of weather is going to occur in your area. Well, this all starts with the sun, obviously, right? So as the earth revolves around the sun, we actually get our different seasons, and there's several reasons for this. First of all, the earth is tilted, right? So we have this, what we call obliquity, or we have this angle that we're tilted from perpendicular. Right now it's 23.5 degrees, but that's not really important to this discussion. Other than, this is what dictates our seasons. So as we go around the sun here, we go from periods of the equinoxes where there's equal amount of, essentially there's direct sunlight across the entire face of the earth. Rather, in the solstice seasons, because of the tilt of the earth, the northern hemisphere, during our summer receives more direct sunlight, and then the southern hemisphere more direct sunlight in our winter solstice during December. And so this is what causes the seasons. And there are large cycles with these events. There's three main cycles that we actually monitor and we can track now. Our path around the sun changes from more of an ellipse to more of a circle. Okay, and that takes 100,000 and also 400,000 years to do that. But to get away from this this is constantly changing, right? One other thing that we do is this angle that I talked about. This changes too on a different time scale, about 40,000 years. And then the Earth also wobbles like a top. When you spin a top, you can see how it wobbles back and forth because of the tides, the sun, and the moon. That sort of affects how the Earth moves, and it wobbles through space. And all of these things can affect climate, but not weather, right? Because weather is the day-to-day. These are large-scale changes that are happening, so we don't worry about this in terms of the weather. What we do worry about is, okay, what is our season? How much sunlight are we getting today at a particular location? And that's going to greatly affect what our weather's like. You guys experience this. Some other locations don't necessarily see these changing seasons because they get about the same amount of sunlight year-round. But we have vastly different seasons, right? Sometimes they're all mixed together even. So, all right, so let's pretend for a moment that we are on an Earth just completely covered in water. There's no land on this Earth. It also does not spin. It's not rotating at all. So you can sort of see here if you're in this is kind of the situation we're talking about, but the Earth's going to be perpendicular, and then so the greatest amount of sunlight is going to penetrate and hit right along the equator, right? And then as you work away from the equator, you're actually going to receive slightly less direct sunlight. And so what this does is it heats up this water, this aqua planet, at a different rate. So you get a lot more heating along the equator and a lot less heating toward the poles here because you have less sunlight. And so what happens is this differential heating, as soon as this occurs, you change what we call atmospheric pressure. You change the air mass, the air that's associated above where this heating is occurring at the surface. And when you heat a surface, you actually decrease its pressure. So we can put a low pressure center here, right? And so at the poles, you'll actually have higher pressure than you have along the equator. And immediately what happens when you create a difference in pressure is you get wind. That's what wind is. Wind is just the movement of molecules from a higher pressure to lower pressure, because the Earth is constantly trying to balance out these differences. And so along the surface, you get the flow that would flow in this hypothetical planet from the poles toward the equator. And because this air here, it's actually lighter, so it starts to rise. And we actually would get this circulation. So you get air in a three-dimensional sense, flowing toward the equator along the surface, rising, and then back toward the poles. So you would get this one gigantic circulation over the Earth. Okay, and this is what would happen if this was aquaplanet, we weren't spinning, and we just got more heating along the equator the entire year. Okay? So now we move from that to, we're going to add land to the surface. And in the northern hemisphere, we have a whole bunch more land than we have in the southern hemisphere. And that causes differences between the two hemispheres as well. But what you get between land and ocean are basically land and sea breezes. So the land will heat up a lot faster during the day. And just like before, when you heat the air, you lower its pressure. So there's higher pressure over the water, and then the wind starts to flow toward the land during the daytime. That's when you get your ocean breezes. If you've ever been to Florida, along the beach, I lived in Miami a lot. I mean, it was just every day, right? So, and then less important, we won't talk about, you actually get the same kind of localized circulation. At nighttime, the opposite happens. The land cools off a lot faster than the ocean. So you actually have higher pressure over land, and then you get the wind flow offshore. And this actually works on a larger scale too. In the northern hemisphere, you got a lot of land, so you have a lot more of these type of processes occurring. And again, wind is just the process of the air flowing from higher pressure to lower pressure. And the wind speeds increase when the pressure difference becomes larger. So the larger the difference between two areas of pressure or air, right, the faster the wind speed. A lot of times you'll wake up in the summer morning, it's nice and calm out, right? And the sun gets a little bit higher, it starts heating up all the blacktop surfaces, the concrete, heats up a lot faster than the trees and the grass. And immediately you get that pressure differences, and then it starts to equalize. So you start getting that breeze about 9, 10 o'clock in the morning, and that's the process that's occurring. So what does the Earth actually do? Well, we know that the Earth rotates. And when the Earth rotates, we get differences, we get a different pattern than what we saw with the aquaplanet. And you don't have to worry about all the details here. It's just to show you what in reality, we just don't have the flow at the surface from the poles to the equator. Because we're spinning, and because we have differences that are between land and ocean heating up, we get bands of different pressure, of higher and lower pressure. And so we get a lot of complex air movement throughout the world. And essentially, all of these processes are just trying to equalize the heating. We're trying to take the heat that we get mostly at the equator and in the subtropics and move it toward the poles. We're trying to stabilize or equalize the temperature across the Earth. And that's essentially what weather is. So how many are familiar with the term air masses or air mass? Okay. What is an air mass? Anybody? Go ahead.
It's basically a large amount of moving air.
Right. Okay. And so how do we know that's right? And that air has a similar characteristic, right? And it might be expansive over a certain area. How do we know where these air masses come from, where they originate? Have you ever stopped to think about, and you probably hear it a lot on the news and the weather in the wintertime, we get a lot of systems out of Canada, right? So we get a lot of areas that, what is Canada, warmer or colder? Colder, right? So we get cold, dry air out of Canada. In the summertime, we get a lot of warm from the Gulf of Mexico. You're exactly right. So you have a good handle of what these air masses are. And so they are, essentially, they're just named for where they come from. And you don't have to worry about the names, but we have maritime air masses. Obviously, anything that's maritime means it's associated with the ocean. And so you got either a warm air mass coming out of the subtropics or maybe cool, moist air coming out of the Pacific, North Atlantic. We get these continental polar air masses in the wintertime, even the Canadian Arctic air masses, which we haven't seen too many over the last 10, 15 years. But anyway, the air masses originate from different places. A lot of times you'll see on a weather map, you'll see fronts, if you're familiar with the fronts. These aren't real things that are, moving across the country, but they let us show where differences in the air masses occur, right? So this is just an example of how a system of two different air masses, the blue represents a cold air mass and the red represents a warm air mass, how these two air masses interact. And we draw these fronts where the differences occur, where there's a change in the air mass. And so this is just, you're probably familiar with this. Where's my mouse here? How a system just moves across the country in 2 or 3 days. And so you get a lot of the cold, obviously the cold air is coming down and replacing that warm air. You might get a warm spring day and then all of a sudden it's back in the 30s and you get real frustrated because you want spring to be here. This is the type of system that does this. So we get that cold Canadian air mass come in and replace the warmer air mass that we had before. All right, so what we're going to do, we're going to take an attempt to draw a little weather map, okay? And we've just provided some basic information that's going to help you to draw this. Now, obviously I've given you very limited information, but on a weather map we connect areas of equal pressure because that helps us dictate what kind of air mass and how large and expansive they are. And so what we've provided you is this worksheet here, and each of these circles represents a weather observation. So this might be an observation that comes in from an airport or an automatic weather station. And we've scaled these down quite a bit. You usually get a lot more information with these, but we're just going to give you the temperature, which is the upper left-hand corner, and then we're going to give you a pressure, and we don't care about the units. We've just know that it's 15 units of pressure, okay? And what we're going to do is we're going to draw the isobars. Isobars are lines. I don't know why that did that. Isobars are lines that connect areas of equal pressure. You're connecting the dots, essentially. So for instance, we're going to maybe start out at 20. So we're going to draw a line right through 20. We're going to go every 5 units. And so you'd have to draw a line. So you see two dots here, 19 and 21. So the 20 would go somewhere in between. And then it would go somewhere in between this 19 and 21. Right across this 20. So now you have 16 and 21, so you might draw it closer to the 21 than the 16. And then this, obviously it would be to the left of the 19 here, okay? So it's going to stay, this is 17, 17, so, oops. So the line would be drawn through here. So we're just going to give you a few minutes to draw all these lines. We're going to connect them 5, 10, 15, and 20.
So you're going to draw lines where the 20s would be? The 5?
Yeah, we're 5, 10, 15, and 20. Actually, I think there's no 5 lines. So we're 10, 15, and 20.
We'll be around to help.
Yeah.
We're looking at the number on the right.
Yeah.
Making a straight line like through.
All right, so I'm going to advance this one slide here, and we're going to see.
Oh no.
Huh?
See the answer?
You want to wait?
Do a reveal. 3, 2, 1.
Okay. Yeah. So this is where they should be, okay? And this is what your isobars should look like. These equal lines of pressure. Now, some of you may have connected this around. That's completely acceptable, right? Because you don't have any more information down here to know. Perhaps this isobar does connect down this way. That's completely fine. Maybe you wanted to draw a circle over here. That would be possible, right? Given the information that you have, but you can, slightly different patterns depending on the amount of information. Now, where does wind flow? That's got a lot. I got two right answers for 2 different reasons. We're going to focus on the direction that wind flows between 2 areas of pressure, from high to low. Okay. So what I want you to do, this is at the surface of the earth, is I want you to draw, and it doesn't. I mean, you can draw several lines if you wanted to, just arrows of the direction you think that the wind would flow on your weather map here. Just based on what you have so far, which are lines of equal pressure and areas of high and low pressure. So if you generally got the arrows moving from high to low, that's the direction that we want. But unfortunately, it's not that simple, right? So on Earth, we spin. How many of you heard the Coriolis effect? Yeah. Okay. So it's just this apparent force that we have on the Earth that when you spin the object and the object travels in what we see as a curved path. You don't have to worry about the stuff behind that. But what it means is that the wind doesn't flow. Now, this is going to look a little bit different than what you've drawn. The wind doesn't flow directly from the high pressure to the low pressure, but as it begins to move, because the Earth is spinning, the Coriolis wants to turn the wind toward the right. So in this way, all of the wind here, as it's moving from the high to low pressure, is going to be turning toward the right. Same thing over here with this high pressure toward the low pressure. It's going, as it starts to move this way, the Coriolis will turn it toward the right. So you get these curved paths of the wind. Okay? So we can recognize the patterns on a weather map about the direction of the wind flow, and that wind flow helps dictate the change in the air mass and where its origin, where it comes from. So if you're in this region, if you recall that little schematic, it was in the red, right? This region has warm, moist air that would be coming out of the Gulf of Mexico over Ohio, perhaps. And this would be the cool Canadian air mass that's flowing southward. And so we can, by these observations, these wind observations, we can see a change in the air mass, okay? So now I want you to take that information, the change of the air mass, and I want you to take perhaps the temperature the upper left-hand corner, okay? So these are just temperatures, say in degrees Fahrenheit, 72, 62, 73, 72. And I want you to draw two lines for me. Okay, so we know that the wind direction separates two air masses. And we can see that the direction here is different than the direction here. So we just want to draw a line based on that information where the change in the flow occurs. Where is the front? That's essentially what we're drawing. Instead of calling it such, I'm just saying you see that this whole area is flowing this way, this area is flowing this way. So there should be a front, a line that we can draw on this weather map based on the temperature and the wind flow of where that line should be. We ready? Yeah. All right, so let's do the next big reveal here, right? So I think you guys picked up on the vast differences in how the wind flows and with the cues of the air mass changes. So you don't have to have the colors, but these are where the two prominent lines should be. So this, on a weather map, we call this a cold front, right? The reason we call this a cold front is because the colder air is behind it and it's moving and replacing the warmer air that's out ahead of it. Now, this is a warm front, so this line here is separating two different areas where you have southwesterly flow and easterly flow. And what happens along this boundary is this warm air is surging to the north and overtaking the cooler air. This is how the Earth equalizes its temperature. Are through these, what we call baroclinic storms, but you don't have to worry about that. Warm air is flowing northward in this direction, but you have to have the pendulum swinging in the opposite direction, which is the cool air coming down this way. And so we look for these patterns. Now, some of you drew a third line, okay? There would be a third line that's attached oftentimes as the storm gets older right here, okay? And it's essentially, we call it an occluded front. You might have heard about it on the Weather Channel or something like that. It's just where the air masses, as it says, it's occluded. It's kind of a mixture, really, of these air masses coming together, and they're not as distinct, but it's very good. Now, there were other things on this map, and a lot of you brought them up. The circles, the amount that the circles are filled in, that's actually cloud cover. So that's another thing that you can look for on here to see where is the cloud cover. It's mostly associated with this low pressure system. We did keep some of the precipitation on here as well, although you didn't have to necessarily use this to show where the rain is occurring. And so the rain is going to occur closest to the system, and then obviously we would get some thunderstorm developments somewhere in this region out ahead of the cold front in this typical pattern. Okay?
Are the number of dots related to how heavy the rainfall
It is. It's exactly, and there are a slew of different precipitation symbols, okay? And the reason that we stepped through this exercise is I wanted to highlight the fact that for a long time this is all that we had to rely on to get a sense of what the current conditions are. Meteorologists at the National Weather Service, every hour on the hour, would start drawing these analysis maps. Every hour, across the entire Ohio, maybe the entire Midwest region. And they have to be drawn by hand, okay? But what we've done, obviously, with computers is we've been able to bring all of this together and do it in a much more efficient way. And computers can help us to recognize the patterns and draw these maps. So we start, this is familiar graphics from the Weather Channel here, so you can get current conditions. The United States is covered in observations, much more than, say, where my work, which is in the Arctic or Antarctica. We have all kinds of observations in the United States, so we know what's going on almost in every location, except for maybe the mountainous regions of the West, right? So we can combine all kinds of variables, temperature, on the upper right's dew points, just to measure how much humidity is in the air. We can put all of this together. Then we step it further. We now have satellites. Okay, so these satellites, we add the satellites and it enhances our information about what's going on. So we can see simultaneously the clouds across the entire region. We're not just worried about where's the observation coming in a little filled circle. We can see what's happening right now, every minute of the day. So we add different types of satellite. We can sense, this is what we call a visible satellite, so you can see the structure of the clouds. We can sense, okay, we can get a sense of how warm these clouds are, how tall they are. And all this information comes together to draw a current surface analysis map, which is what you just did. Obviously, they have some fancy graphics. They pay a lot of money for that and to do this.
How long ago are you talking, the difference between drawing it and basic sense of
Right, so I mean, a lot of the I should say, drawing is still done. It's just not done as routinely as it once was when they didn't have the computer models to drive this information, to put it all together. So it still is done on a regional basis and depending on the type of situation, but it's not as mandatory because we have a lot of information feeds. So I mean, you're talking about even as recently as early 2000s, it was still being drawn. So what we're able to do is take all that information. Now this is what it looks like to us. So we just have what we call our rapid update model, or just a model that the computer takes all the wind observations and all the pressure observations and throws them into this set of initial conditions. Just tells us what are the conditions like. And what models do is they take these mathematical relationships, these physical relationships, known physics equations, and mathematical relationships, and solve all of them simultaneously across the entire region, adding all the information, the temperature, dew point, to get a forecast. So we're able to get a lot of forecasts repeatedly throughout the day, every hour on the hour. To recognize weather patterns, right? We can look at the satellite. We're here in Ohio. We can look upstream using the satellites to see what kind of weather pattern we're in, Is most of our flow coming with the Canadian air masses? Is our flow coming out of the Atlantic? I mean, this helps us recognize the patterns that are occurring. We can see the patterns in the tropics, right? The tropical, this is where most of the Earth's sunlight reaches directly, so we get consistent thunderstorms rolling across the equator. So we're able to use these observations to see and look at the patterns throughout the entire globe in terms of weather. All right, so we're going to jump now to the topic of climate. Related, but different, right? So climate can be thought of as the average weather over a period of time. And this period of time is an important concept because depending on the length of time, you get a different answer, right? So it's this long-term average of temperature, precipitation, the average weather conditions over a particular area. And we use a 30-year window in terms of when you hear our normal high temperature today is, say, 80 degrees. That's what's happened. It's the average temperature from 1981 to 2010. That's our current normal window. Okay, in 2020, that will change. It'll be 91 to, 91. In 2021, it'll be from 91 to 2020. That'll be the new average period. So this actually fluctuates. It changes. Yes?
Is there a significance to 30 years and why that's used?
That's a very good question. Do you know the answer to that, Jason? I don't either.
Oh, sorry.
Wow.
I mean, it was probably chosen at one point in time, but
Do you know?
Doesn't it have to do with solar maximums and solar minimums? Aren't they on, doesn't the max and min run on a one wave?
Yeah, but it's about 11-year cycle. So, I mean, you're talking about the max and min with the solar activity?
Right, I thought it was more of a 14.
Yeah, it's 11 years, so that wouldn't, I mean, it wouldn't match up precisely, but
Maybe about 3 cycles of it.
yeah.
Would that maybe allow you to get like a good average? Maybe could one set of 11 years be a little warmer, one a little colder, one a little warmer, they'd average out to be
Sure, but
a good
then
idea?
that brings up a good concept then. Then why stop at 30? Why not do 50?
I
Because
don't
then
know.
I know, no, that's why I'm,
Like, I just put 3 times 11.
you're absolutely right. 3 is better than you know, 2, so is 5 better than 3? And so it really depends on the period that you're looking at.
And
So
I guess if you go an odd number, is it going to be skewed one direction? If your odd happens to be 2 warmer periods or 2 more maximum periods, is your average going to be slightly skewed warm as opposed to cold, cold, where it would be skewed colder?
sure, and if you get 2 really extremely hot seasons, that could slightly skew the temperature normal in one direction or the other. And so it's very, it's very good questions about why the 30-year frame. But I'll get the answer to you somehow this week for sure.
Okay.
All right.
Super. Thanks.
All right, so what factors control the climate? We looked a little bit about the weather factors. What do you think controls the climate? Just land? You said land? Yep, absolutely land. Water. How close are you to water? How much precipitation are you going to get? What about your location that's special? In Ohio. Latitude, right? Altitude, elevation differences.
Weather patterns,
Yeah.
like El Nino.
Yeah, weather patterns, prevailing winds. So these are all factors that go into what control the climate. Latitude, also vegetation. I think you had that experiment this week, right? About the temperature sensors in the forest compared to outside in the sun or in the shade. So those are all things over a long period of time, those are going to affect the type of climate that you have. So the climate system, again, long-term average condition of the atmosphere. And we might say in a very technical way that Ohio has a humid continental climate, okay? I think that sums it up. We're not really close to a large body of water. We have the Great Lakes, and that certainly affect our climate. But it's mostly the continental air mass we talked about, and very humid, right? Especially in the summertime, we get a lot of moisture. So that's a technical term. But what about the climate system in general? I mean, we talked in the last little segment just about the weather, the precipitation, the clouds, and its interaction with the sun coming in. But there's a lot of components to the climate system. Not only the atmosphere, but we have all these exchanges happening, all these heat exchanges, differences in temperature between the ocean and the atmosphere. Over land, we got changes that are happening in the soil. We've got large areas of ice, right? The Arctic and Antarctic. These help regulate the climate of the Earth. Without these, we would be much warmer. And so we have all of these very complicated systems and processes that have to be brought together and understood in a way, okay? First of all, with just understanding what's happening in the climate, then we have to somehow model that to see what's going to happen into the future. And so I'm going to pick one of these components. I'm just going to talk about the sea ice, okay? So how do we observe the state of the Arctic sea ice? This is a photograph, a picture of the HMS Investigator in 1853 in the Northwest Passage. Does anybody know where the Northwest Passage is or heard of it?
Yeah.
Okay. So this Northwest Passage is north of Canada in the Arctic Ocean. So this was actually a ship that sunk there in 1853. So it's a very dangerous area to try to sail through because it's literally clogged with ice, right? But how did we know what it looked like in 1853? How did we know what it looked like in 1950? Okay, so we rely really heavily on shipping records that go back primarily to the mid-1950s, but we have some records, obviously, that go back to the late 1800s and explorations and that sort of thing. So just the observers, the few adventurers and the observers that were there. I think earlier this week you talked a little bit about proxy records, I think ice core records, right? We can use these ice cores records to determine, what sea level was like, how cold and warm was the Arctic. And I think you talked about, the Thompson's Ice Core Group at Bird Polar. We can also get ocean sediment, so we can get cores from the ocean sediment. We have Leonid Polyak, he's our principal investigator in charge of the ocean sediment group at Bird Polar. So we get a lot of information about distant past climates from the ocean core. And you can also look at plant material that's in the bottom of the ocean. This biogeochemistry group, Joel Barker spoke earlier this week, right? The mummified wood in Ellesmere Island, it gives us clues that the Arctic used to be warmer, used to be a lot warmer, used to be ice-free. Maybe it's as soon as 5,000 years ago, and certainly during the last, what we call interglacial or warm period, the Eemian, about 125,000 years ago. They have evidence of ferns, right, in the Arctic ocean floor. Different plant material and stuff was around this time. But in terms of records, how do we observe the state of the Arctic sea ice? So we're going to do another activity called predicting the sea ice extent. Now, sea ice extent essentially is just how much of the Arctic is covered by sea ice. And by sea ice, there is a certain percentage that they use. But we're just going to give you a little bit of information at a time, and we're going to step through how do we know, what was it like, how were the conditions changing, and how would we know what that would look like in the future, right, at different periods throughout time. So Jason's going to pass out these little cards. Keep them closed. All right, so this is the information that we have from the early 1950s through the early 1960s. And I took the units off of this. This is just a standardized scale here to show you how much sea ice extent, these standardized anomalies in the early 1950s and 1960s. So what I want you to do is I want you on this piece of paper here on the front, I want you to draw what you think maybe the mean of the next 5 or 10 years might look like in terms of sea ice extent. So this is a line graph. This is actually monthly anomalies, so you can see there's a lot of variability. I think you talked about variability around a trend or around a mean earlier. This is kind of just this running mean of these monthly anomalies here. So this is about 10 years of data of what we know that the sea ice extent in the Arctic looked like from the early 1950s through the early 1960s. Yeah.
Do you want us to draw the monthly anomalies or the
Just draw the mean, I think. Just draw generally what you think. Do you think it's going to stay? The kind of the broader question is, do you think it's going to remain the same? Is it going to go up? Is it going to go down?
is it the amount of sea ice?
Yeah, this is amount of sea ice extent.
How many years do you want us to do?
Just do the next 5 years. And then think about, too, why are you making that conclusion? What information have I given you or not given you?
Can we bring prior knowledge into this?
Sure, you can. I mean, if you have prior knowledge that shapes your perspective, I think that's a good thing to look at. So in the interest of time, we probably have to move a little bit. I have to move ahead. I'm just going to step forward. So how many think that the ice is going to stay the same? How many think it's going to grow? How many think it's going to shrink? We're going to have less in the next 5 years after this. Okay. It went up. Now, what information if you think about it, what information did you really have to make a conclusion that it's going to go up, down, or otherwise? All we had at this time were ship observations to rely on what's happening in the Arctic, or personal observations through field campaigns. That's all we had, right? So now we get into the late 1960s. This is a satellite era, right? We start sending satellites into space. We can detect what's going to happen. So what I want you to do now is I want you to think about what's going to happen over the next, I forget what we did, 10 years.
So you can open it up. Don't completely open the paper. Just open the top like a greeting.
Just flip it up once. Okay, and you're going to get the update, right? Actually, we updated a little bit further. So we went to here. Okay? So now this early period of satellites showed us that the sea ice started declining, right? Really steeply since the late 1960s. So we have that information. Predict the next, we went 20 years.
Is it fair to say that the earlier information wasn't as accurate because you were relying on things like shipping records and
I think that it's fair to say that it's less accurate than now, but is it inaccurate? I don't think. I think we can't extend that far. Basically, science is what we know at the time that we measure it. But
not as accurate as
I would make that conclusion, yes. 5,500 years ago?
5,000.
Yeah, 5,000 years ago.
No ice.
Or no, 5,500 years ago where we are now. Like our sea ice extent now, just giving a little bit away, is where, they have evidence that 5,000 years ago it's at the same level.
Oh, okay.
But 125,000 years ago, there's plenty of evidence that said there was no sea ice. We had alligators, we had ferns, we had all that stuff in the Arctic.
So Joel Barker, when he was here talking about what it was like when there were forests.
Completely different environment, yeah. But that's 125,000 years ago.
Okay.
Distant past.
You made it's a good connection.
All right, so based on the information that you have here, the next 20 years you think are going to do what? Decrease, right? And you actually have heard a lot in the news what's happening. So this takes us into, the mid-1990s? You sort of see it here, right? If I was looking at that, I'd say, okay, it's a little bit steeper in this segment. It kind of starts leveling off here. All right, so now you can flip which direction, Jason, flip it over?
Yeah, if you just open it up all the way.
Yeah, open it up all the way and you'll get the information to there. Now what's going to happen? Up, down, decrease, right? So we decrease a little faster, and then in the last few years we'll just speed it up a little bit, right? We're tanking. But if you also notice back here we had a lot of monthly, what we call variability, a lot less, and now we're back to this very high variability period, right? So this year, the sea ice is actually just poking along, right? It was a different type of winter in the Arctic. The sea ice extent, right? The amount that it recovered was actually above normal if you base it from a 1979 to 2000 mean, all right? There was a story, they have this little city near Fairbanks where they actually have a citywide lottery to dictate when the sea ice is going, or the river ice is going to break up, and they just have this contraption that when it tips over, they win the lottery. So this was the latest ever recorded this year, and it's because the Arctic had a very cold winter, and so you can see that even in a general global warming climate, a warmer climate, you can get a lot of variability, and this only goes to 2010. So 2012 sea ice last year was actually here. Okay, now if this is initially all the information that we had, right? Sea ice extent, how expansive is the sea ice? But we actually have a lot more information than that now, because we do remote sensing of the Arctic. This is just one satellite that's up there. It's the AMSRI instrument on the Aqua satellite, but essentially, it uses microwaves, and not the kind you have in your kitchen flying through space, but just the frequency of the microwaves coming down. And they're sensing, they're getting an idea, a picture of what the sea ice extent's looking like. But we also have active sensors where we shoot LiDAR, we shoot essentially lasers that come down, and they can measure differences in both the sea ice extent. So, this is all covered with 100% sea ice, and this is in 1972, 1974. Okay, this was the minimum. And you can see in here, the Northwest Passage is actually blocked. So you can't get through. This is called the Northern Sea Route here. It was also blocked back in 1974 at its very minimum. Okay? But this was last year. So you can see the Northern Sea Route here along the Russian border, completely open. You can see the Northwest Passage is completely open. And this is the least amount of sea ice that we've had in September since the satellites began. All right? And that's all, right now that's what we can say based on the satellites. Is in our lifetime, this is the least amount of sea ice that we've seen in the Arctic. But we also have more than just sea ice extent now. We can look at things like sea ice age and sea ice thickness, which add more information. So we get sea ice in other dimensions. So this is just using a satellite to estimate how thick, and this is in meters, how thick that the ice was in February, March estimate 2004 to 2008. So here's Greenland, here's Ellesmere Island, northern Canadian archipelago, Eurasian continent over here. And so the bright red, very thick ice, 5 to 6 meters thick. A lot of this is much smaller, 1, 2, maybe 3 meters thick, right? This was just in 04 and 08. So the last measurements last year from a new satellite, European satellite in 2012, this was the estimate. Okay, same scale. So you can see a great decrease in the amount of ice volume. So not only is the sea ice extent changing, right, but we have a lot thinner ice. And so what that's leading to is repeated cycles where we get even additional sea ice melt each summer. And my guess is, even though we've been tagging, kind of going kind of slow, right, throughout this early period of melt in the sea ice this year, because it's so much thinner, it's not going to take very much to tip it back toward, rivaling with last year's record sea ice minimum. So we have all, the good thing is we can get additional information from different sources, and satellites are really a huge key here. So I don't want to bore you too much with the global climate modeling, but obviously we have to be able to model all this stuff. So we take the climate system and we put it on some type of grid. We just represent large areas of the Earth in computer models, and we solve thousands of lines of mathematical relationships, and it's very computationally expensive. And global models tend not to be optimized for regions of interest. So they're kind of broad scale. We're trying to get what are the climate projections going to be like? And we're using the large forcings. Where is the sun? What's our position in those cycles that we talked about earlier? And we also have what we call this parameterization problem, okay? So we can't represent all these physical components explicitly. We can't model them because we don't fully understand them, first of all, and we don't have enough computer resources. So we have to add their effects to the model. And so sticking with the sea ice, one of them is clouds and land surface, but sticking with the sea ice, this is just a few of the different processes that are occurring. So as you get, warm water, or the warm Gulf of Mexico water flows north near Greenland, right? And then it cools off. And as it cools off, the fresh water on top will freeze. That leads to this process called brine rejection, so you get saltier water. That changes how the ocean dynamics, and you may have heard the thermohaline circulation. And so these are all important processes that are very difficult to model, okay? So, but we're getting better. That's the good thing, is that this is, it's difficult to model the sea ice. And so if you guys are familiar with the IPCC report that you've heard about probably in the news. And so the last go round in 2007, the black curve, this is just a line graph just showing the amount of ice, again, ice extent in the Arctic. The black curve is what we've actually observed. It's the same line graph that you saw before, just on a different scale here. And so before, all of our best models in the world projected this change, this blue line, okay? And you can see this much slower change, this slower decrease in the sea ice extent than what we're actually observing. Now we've been able to improve that the latest go round, the report that'll be out later this year, but we're still, in our models, are still not melting the sea ice as fast as we're seeing it now. So it's kind of a scary thought that all of our climate projections that you hear about, 1, 2, 3 degrees C warmer, we're still not catching up to a big regulator of that climate, which is sea ice. We're losing it faster than even our models can predict. And so it really raises the question of how confident can we be in the future projections on either side? Are we over-predicting? Are we under-predicting? And we have to continue to get better and improve this analysis here. This is a nice schematic just showing the amount of information that goes into it, has gone into it since the mid-1970s. So we start out with just the atmosphere model, then we start adding things into it. We get bigger cities in the models. We get maybe a thin ocean that just has one layer. As we learn more about the ocean, we can get different levels of the ocean along with everything we had before. Then we start getting processes from factories and the urban development, and then also interactions with gas molecules in the air. And so you can see as we learn more, we can make better projections about the future climate. So I'm going to try to wrap this up and tie it back in with the polar regions, because this is directly what that I deal with. And so kind of the motto with the Polar Meteorology Group at the Bird Polar Research Center is an understanding of polar weather and climate as part of the Earth system. These are distant places we've been talking about today, right? The Arctic and then also Antarctic. Most of you don't care what's happening in Antarctica when you wake up tomorrow, right? It doesn't really have a bearing, certainly not on your immediate weather, but it does on the climate and on the state of the Earth into the future. And there's big differences between the Arctic and Antarctic that, up until the satellite era, we knew about, obviously, and explorers could tell us the differences in the environment, but we couldn't see them. We see them now like we've never seen them before, and so we can see these large, expansive areas, and we know, that these environments are vastly different, although they obviously are covered in ice. And because, Antarctica is a landmass that sits on the South Pole with sea ice around it, its sea ice disappears every year. Every summer, the sea ice disappears, and it grows back in the winter, or into our winter, in their summer, okay? And so what we're starting to see is the Arctic sea ice look more like the Southern Hemisphere sea ice, where we're going to lose it in the summertime, and then it's going to grow back in the wintertime. But there is no land here at the North Pole in the Arctic, right? This is just sea ice sitting on top. And so this creates very different weather patterns, and weather patterns and climate, and that's what we study in my group. This is McMurdo Dry Valley's region. I don't know if anybody's talked about it this week, but this is a very peculiar, very different region of the Earth, unlike any other. Very dry place in Antarctica. You can see that it's snow-free. And a very difficult environment to model. And so we take what I talked about before, these global climate models, and we scale them down to very high resolution. So we get a lot more of those grid boxes, a lot more of those small little areas to kind of depict what's happening. We actually create a land surface and put it in the model. This is a McMurdo Dry Valley, to tell the model what it looks like. And it's, again, a very difficult place to model, but that's what we're doing in our group. And I just want to end with this. So how does Antarctica impact your life, or how will it impact the lives of humans moving into the future? So we've known for a number of years now that Antarctica is warming, like a lot of places on Earth, especially in the springtime and in the wintertime. But with average wintertime temperatures around minus 50 degrees in the wintertime, I mean, a little bit of warmth obviously is not going to change. You're not going to melt the ice and that sort of thing. Okay? But there's this area, what we call West Antarctica. And in what we've found in the summertime, since the late 1950s, is this steady trend toward higher temperatures in the summertime. And what does that impact? Well, again, overall, at this station, this bird station, we had this record 2005 heat, relative term, right, minus 10 degrees C. But a lot of the areas around this station were above freezing, okay? And you get these small, short periods of time where you do get freezing, but this was a very expansive event, right? We know that this peninsula region is warming, and we're getting a lot of melting there, but we experienced a lot of surface melt here in Antarctica. And that water directly goes into the sea level, and the sea level rises, right? The Gulf Stream on the east coast of the United States, it's warm water. It's more expansive. So sea levels won't rise equally across the entire globe. Some areas will rise more than others. And so they're really concerned along the east coast. We work with the group, a naval group out of Virginia, and they're wanting to build the port into the future that can sustain, and they're looking at basically building their port 10 feet, 12 feet higher than it currently is to anticipate some of the sea level change that's occurring. So I just want to end with a quote. It's actually an introduction for my PhD dissertation that I think is important. Is there's a lot at stake in understanding Southern Hemisphere climate. Climate change challenges the human population like never before, and rarely are its effects linear. The multitude of feedbacks involving the Earth's surface, energy exchanges between the ocean and the atmosphere combine to influence weather, climate, and drive circulation patterns across the globe, like we've talked about today. Yet with all these processes occurring above, below, and around us, we often neglect what we do not directly experience. We ignore the basic principle that we are connected to the distant places through climate, and changes occurring in Antarctica have far-reaching effects elsewhere on the Earth. So with that, I think, any final questions, and we'll wrap up.
I want to compliment Aaron. His group by far has the most abstract
Thanks. So, yeah.
So you talked about sea level rise not being equal all over, and I
Yes.
think I have a very basic understanding of fluid dynamics.
Yeah.
And it's hard for me to understand how it could be that, you know, sea level rise could be 10 foot in one area and 2 inches in another.
Yeah, there's a lot
A
of
little bit about that?
Yeah, there's a lot of dynamics that go into it. Obviously, the big thing is what is the shelf, you know, what does the continental shelf look like, right? Does it raise, does it come up quickly? Is it shallow? So that'll affect how quickly the levels rise. The Gulf of Mexico water is warm. And so thermodynamics will tell you that warm water, like warm air, takes more space, okay? So it's already expanded in terms of the warm water. So if you increase its temperature even more, it's going to expand more. And then you're contributing to the volume. And so, yeah, I mean, I think that like I said, that's one of those effects that's nonlinear, because everybody thinks global warming means it has to warm up equally across all areas. And that's simply not the case. We get some glaciers that grow in global warming scenarios. It's just something that people don't think about, but you know, you get more precipitation, but you raise the temperature only a little bit, you're going to get a bigger glacier. So like with the ocean, there are areas of the ocean that are warmer that will expand quicker than others when you add the volume.
I have a personal, like, weather question.
Yes.
Didn't think I was silly. So I'm curious about, like, this summer feeling so cool and
Yeah.
with relation to like last summer. And do you know, like, with your work, why is that related to the climate, or is that just specific, is that more weather because it's just from your year?
If I told you we have a slightly above normal summer so far, would you believe me?
See,
No, seriously.
Compared to last year?
No,
No.
compared to normal.
Compared to normal?
So last March, we just blew it out of the water, right? We had the warmest March ever, 12 degrees above normal, and that's just unheard of. And it was warm all, you know, most of the summer last year, but we've slowly dwindled the drought that we only experienced a small bit of. But the Midwest has really scaled back through repeated series and a change in the overall weather pattern. And so the heat is really not as expansive. It's different than last year. But May was slightly above normal compared to last year. And we're right.
10 years ago, we're about this temperature.
Yeah, I mean, that's, that's, climate change in Ohio is been felt in two main regions, or two main, I guess, areas. One, nighttime temperatures. So in the wintertime especially, I should say winter temperatures and nighttime temperatures, because those minimum temperatures are not nearly as low as they used to be, and our wintertime temperatures are generally not as cold. Our summers have been, they're highly variable, and I think the last few years have shown that. Even the winter is variable. I mean, 2009, 2010, we had very cold, snowy winters. Last year, we barely had a winter. I mean, 5 inches of snow, I think, all season. And so, yeah, it's interesting that I think I get this a lot, from my parents that'll tell me, well, the 50s and 60s and 70s were so cold and snowy, and they're absolutely right. But then I would ask them, have you ever asked your parents what the 30s were like? Because that was a period of extensive drought. We had several years of drought. We had a lot of heat, and we had another drought and heat period in the 50s as well. But we tend to latch on. We have short-term memories, right? What has the weather done for me lately, kind of thing. And so we forget, to put it into context, and that's what we try to do, is just to put it all into context.
We were talking about the snowy winters. I remember as a kid, I was born in the 80s, but as a kid, we had lots more snow than I've ever seen, as an adult.
Yeah.
We always had a white Christmas, and it seems like the snow comes later now.
Yeah. And the other interesting thing is that, so this, I'll take a good one that people know, the blizzard, right? The blizzard, okay? And, right. 12, 13, 14 inches of snow. That's it. But 78, 80 mile an hour winds, some places the houses were buried, right? We've had at least 4 events crush the snowfall amount. We had a 20-inch snowfall here in, 94-ish? We had several, right? we actually see bigger storms now. Right now we're in a period where we get a lot of variability and we get these large storms. But because I think, this is my view, and I have, scientific basis to believe this, is that our weather is more variable, right? So we go from a March 1st 20-inch snowfall to 80 degrees. I remember it was actually December of 94, so I think 08 was the one, but December of 94, we had a foot of snow around Christmas time. We had 9 inches of rain the first week of January. It's gone.
Right.
Before, snow fell in October, November. We had a little bit through May. And that's essentially what it was like in the 70s. So.
But that may have happened in the past, and we just don't really remember that.
Yeah,
Is variable then? You know what I mean?
Yeah, overall, I think the variability has increased. The sea ice plot, I think, shows it. We had a lot of variability in the 50s, 60s, less, and now we're very highly variable again. I think if you looked at a lot of different variables, even beyond the sea ice, you'd get similar behavior. But we officially started taking records in the late 1800s, officially. What about the 1700s, 1600s? We have to rely on these proxy records, these ice core records, these sediment records, to really get a handle of what the climate was like. But to get the day-to-day weather variability, we eventually lose that information. Even in the ice cores, you start losing annual layers the further you go back. Then you start having to look at decades or centennial scale. So it's the best we can do, I suppose. So.
Keeps meteorologists employed.
Yeah, even when we don't get derecho events correct and that sort of thing. I was going to start out with a little slide, and it's slightly insensitive, and there were people, obviously, when weather comes through. Then that actually is another, I guess, personal antidote. I get excited about thunder snow. I get excited about tornadoes. It's not that I'm excited that people are getting hurt, obviously. But there's this photo, had some lawn chair equipment. One chair was over, and it said, "Never forget derecho 2013." Right, we can laugh about it because, it was fine. There were some areas, with 3 tornadoes in western Ohio. There was some serious damage done, but it just brings up how difficult, and I think drawing these weather maps, it's not necessarily an easy thing to do.
Why do we still get it so wrong? When with all this, it seems like it's not really getting better. The predictions are, if I was out of town last year when the whole derecho thing went through, and they were like, well, it wasn't even on the news, and then this time it was like everywhere.
Yeah. Well,
and then it didn't happen.
Here's another little story. So this spring, every spring, the Ohio State Meteorology Club, which is run by the undergrads in the meteorology department, they host a severe weather symposium. So Seth Banal, he's a forecaster at the National Weather Service, did a little, he did a segment on last year's derecho event because it was a very significant, huge event. And basically we use these statistical database that takes all the information from that atmosphere and tells us what's the statistical chance that a certain severe weather event is going to occur. So he gave this presentation. Of course, this is also attended by a lot of the local media, the FEMA, that sort of thing. And all of a sudden, I hear a local weather channel or local weather personality say, forecast 2 days in advance a derecho event, and people are going to be without power for a week. That is just crazy to me. It's nothing but hype. This is absolutely my personal opinion. It's too much hype. And somebody asked me last week, what did we used to call derechos? I said, a line of thunderstorms, right? Because that's all the public ever knew that it was a line of thunderstorms. It wasn't a derecho, but because we're so weather sensitive, after El Reno tornado and the Mora tornado in Oklahoma, I think, unfortunately, the media sometimes jumps on that, and they jump on it for ratings. Let's be honest. They're competing with the other markets. And so they forecasted this derecho event. Yes, the bells and whistles went off in this program that says the atmosphere is right for a derecho, okay? But there's a degree of forecasting. We can say the conditions are right for something, whether it materializes or not, it's all based on probability. We give a tornado watch because the conditions are right for a tornado. Doesn't mean a tornado is going to occur. So it's a lot of the weather forecasting is based on probability of an event happening. And is it, where do you draw the line between being too informed so that you're hyped or not informed enough? And quite honestly, we never get it right. There's always a complaint there. I forecasted a sunny day today in the mid to upper 70s. I'm not going to get thanked for that. It's perfect. It's spot on, right? It's easy to forecast. It's, it could be easy to forecast. I got up, I told my roommate the night before last that it smells like rain. I'm like, it's not going to rain. It's not going to rain. And I woke up to the rain hitting the window and waking me up. And I was cussing, actually. So I was like, you've got to be kidding me. It's like this small little boundary, this difference of a small little front, small scale front comes through. It's 2 inches south of Dayton, It didn't rain north and west of town. Dublin didn't get anything.
Just a little spot. I mean,
Oh yeah, absolutely. So if the conditions are right. So
Monday's forecast for Tuesday and Thursday were supposed to be perfect, and of course today's perfect for the class. But yesterday when we weren't in class, I was pretty tired from the rain.
yeah, so
Ours is forecast.
yeah, and there are periods of time. Well, and I can't be accountable for everyone, but I do give a Facebook forecast, and I get it right most of the time. So, but yeah, it's a very difficult thing to do, and the more sometimes okay. In models, we can only model what we understand. So the more we understand, then the better our models can be. But if we can't understand, the processes, small-scale processes occurring in individual clouds, that's the new frontier. The more we know about, the better the models can be. So it's a symbiosis between observing the weather, understanding it, putting in the models, then the models driving the science. So it's this back and forth relationship. So. Hopefully it'll get better, but we'll see. I'm a bit over time, so.
Thanks, Aaron.
Yep. You're welcome.